Alright, welcome. In this video today, we're going to be looking at complex numbers. Alright, complex numbers, and we're going to have a lot of fun. Alright, nice. So you're probably wondering, what is this complex number? What is this complex number? So on complex, right, it's very easy. Now before we start with complex numbers, we just want to review the real number system. Once we review the real number system, we'll appreciate complex number a little bit more. So let's start with the first set of numbers that we have learned. The first set of numbers that we learned are natural numbers. So the first set of numbers that we learned are natural numbers, denoted by n. And natural numbers are just positive whole numbers, counting numbers. That's natural numbers. 1, 2, 3, 4, 5, 6, and so on. These are natural numbers. 1, 2, 3, 4, and so on. Natural numbers are just counting numbers. Then the next set of numbers that we learned are, yes, whole numbers. Next we learned is whole numbers, denoted by W. What are these whole numbers? Whole numbers are just natural numbers, including 0. So that's whole numbers. Alright, so that's our whole numbers. After we learned whole numbers, the next thing we would have learned are integers. Yes, you're right, integers. Now, what are integers? Integers are just positive and negative whole numbers. Positive and negative whole numbers. This is when we start to learn about the negative 5, the negative 6, the negative 7, stuff like those. Those are integers. Integers, not denoted by I, but denoted by Z. And integers are positive and negative whole numbers. Negative 1, 0. Let's start from negative 2, negative 1, 0, 1, 2. The dots just mean continuing. So those are integers. Then what next did we learn? Now, there are some numbers that are like fractions, don't it? Yeah man, what do we call those numbers? We call those rational numbers. That's the next set of numbers we learned. Rational numbers. Alright, and rational numbers are denoted by Q. Alright? So denote rational numbers by Q. You're probably wondering why Q. I don't know. Alright? Well, denote rational numbers by Q. And rational numbers, these are numbers that are fractions. Alright? These are numbers that are fractions. So like a half, 1 over 3, 1 over 4. Those are rational numbers. So this is how we write rational numbers. Rational numbers are numbers that can be expressed as a number, the numerator, divided by the denominator, where the denominator is never 0. That's how we write rational numbers. Alright? So select some examples of rational numbers. Negative 1 over 3, a half, 2 over 7, and stuff like that. Those are rational numbers. After rational numbers now, the next set of numbers are irrational numbers. Irrational. Now if rationals are fractions, what do you think are irrational? Not fractions? Alright, not fractions. Now irrational numbers, these are numbers that are exact. These are numbers that we have to leave in their exact form because you can't put it in a fraction, keep on reoccurring. The decimal place keep on recurring over and over and over and over and over and over and over again. Those are irrational numbers. Okay. So irrational numbers often denoted as Q prime or I. Those are irrational numbers. And irrational numbers are like pi. Pi is irrational because what is the exact value of pi? 3.145, continue, 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 never ending. E 2.71 and never ending. And then we can continue, maybe root 7 and stuff like that. Those are irrational numbers, all right? And then all of this can be put in a big set, right? So let's put this in a big set, because so far what we see is that natural number is a subset of whole numbers. Whole numbers is a subset of integers. Integers is a subset of rational, and rational is not a subset of irrational. No. All right, so we're going to put all of this, right, in set form. So putting all of this in set form, all right, so we're going to put all of this in set form. We start with our natural numbers. All right, this set represents natural, and natural numbers 1, 2, 3, 4, and so on. Now, whole numbers, all the natural numbers are in it, but just with 0 included. Yeah. Then integers, we have integers. All of the whole numbers are in integers, and now we just need to put the negative numbers, and so on. Then now we have rational numbers, because yes, when you think about it, a number like 2 can be written as 4 over 2, don't it? And so all integers can be expressed as a rational number. See it here, the number 4 can be seen as 8 over 2. So really, all whole numbers, all natural numbers, all integers are rational. So that's Q. Now on the outside of this set is Q prime. Alright, irrational numbers, because irrational numbers can't be any of these. Now what do we call this entire set now? What do we call this entire set representing all of these numbers? We call this entire set the real number system. So we call this entire set R. We call this the real number system. Now, as we call this the real number system, so the real number system R just encompass all of this. Alright? So the real number system R, the real number system can be written as rational number union irrational number. And that gives us the real number system. This is R. So we call all of this R. Now my question to you is, okay, now that we've discovered and talked back about all of the real number system, where does this complex number fall in place? We still can't see where complex number fall in place, right? It's still not clear. Now let's have a go at this here. If I had given you this question to solve, let's say you're supposed to solve x squared minus 25 equal to 0. Yeah? Solve this equation. Pretty easy. Difference of 2 squares, so we factorize, and we say x, 5 and 5, plus and minus. So solving it, we get x equal 5, or x equal to negative 5. Cool. Alright, following up. So these are real solutions. Alright, so this is telling us x is an element of R. Those are real solutions. Now the trick now, the real deal we want to ask is, look at this now. What if I gave you this to solve? What if I gave you to solve x squared plus 8 is equal to 0? I gave you to solve x squared plus 8 is equal to 0. Now this look, wait. If x squared plus 8 equals 0, and you bring it over, you get x squared is equal to negative 8. Yeah? And so this will tell us that x is equal to the square root plus or minus of negative 8. Now, my question is, what's the square root of negative 8? Absolutely no idea. We don't know how to square root negative 8. Like, that's crazy. How do we square root negative 8? So that's the $1,000,000 question of the day. How do we square root negative 8? Crazy. Alright, so try it. Put it in a calculator. The square root of negative 8. As you put this into your calculator, the square root of negative 8, your calculator is going to say math error. Alright? Your calculator is going to say math error. Your calculator cannot compute it. This is the need now for complex numbers. This is the need for complex numbers. What is this complex number? We cannot square root negative number, alright? We don't have any idea of how to square root a negative number, alright? But we know it can be computed. Think about it. If it's a number, shouldn't be able to square root any number and get a result? Yes. But since we don't know as humans what's the exact value of these negative numbers when you square root it, we don't know what happened. Let's just do some little bit of algebra. What if the basic number that you can square root, negative 1, what if when we square root negative 1, what if we just call this I? Right? Wouldn't this make things easier? Yeah. Like, look at this. If we call the square root of negative 1 I, alright, I can just represent the value of the square root of negative 1. We don't know what I is, but let's just call it I. Because look at this now. Wouldn't you then be able to square root numbers like negative 9? Because by going back to thirds, we can break up negative 9 as maybe negative 1 times positive 9. So the square root of negative 9, now we could write that as the square root of negative 1 times the square root of 9. But the square root of 9 is what? 3. And the square root of negative 1 is I. So look at that. So the square root of negative 9, the square root of negative 9 is just 3i. This is the need for complex numbers. Complex numbers will allow us to square root numbers that are giving us negative value. And that's where this whole idea of complex numbers come into play. Alright? So far we've learned the real number system, but complex number encompasses the whole thing. So now let's talk about complex numbers. Alright? Now we can start talking about complex numbers. So, a complex number is represented in the form z, and z is equal to a plus bi, where a is the real part of the complex number right, and so the battery died, and so now we had to restart over, but no problem. So now we can start. So now what is a complex number? So a complex number now So what this is saying is a complex number is a number, and generally we call a complex number z. So a complex number z is equal to a plus bi. A complex number z is equal to a plus bi, where a is the real part. A is the real part of the complex number, and b is the imaginary part of the complex number. A is the real part, b is the imaginary part. So just a typical example, look at this. If we were solving x squared plus x plus 1 equal to 0, we're just looking at a simple quadratic. If you're solving this quadratic equation right here, right? And remember what we said is what did we say we call the square root of negative 1? Remember, I is equal to the square root of negative 1. Always bear this in mind. So if we're solving an equation like this, we end up have x is equal to minus b, negative 1, plus or minus b squared minus 4 times a times c divided by 2 times a. That's how we would solve that quadratic here. Now when we do this, minus 4 times 1 is 4. 1 minus 4, so inside of here would make this work out to be x is equal to minus 1 plus or minus 1 minus 4 is negative 3. So this would be what we're getting for x, right? So we just want to show you how this real part and imaginary part come about. Now when you're going to write this down, right, we know from surds, right, we can break up root 3. We can break up 3 as the product of two numbers, negative 1 times positive 3. So we can write this as minus 1 plus or minus the square root of negative 1 times the square root of 3 over 2. Right? Now this square root of negative 1 is I. That's how we define a complex number. Remember, we don't know what is the square root of negative 1. We don't know what is the square root of negative 1. Right? But we can call the square root of negative 1 I. Just give a value I. So in this case, x would be equal to negative 1 plus or minus the square root of 3 times I over 2. Breaking it up as a proper fraction, this would be negative a half plus or minus root 3 over 2 times I. Now you see this negative a half right here? This is the real part. Notice we say how a complex number look. Z is equal to a plus bi. That's the standard form of a complex number. A complex number is any number that can be expressed in the form a plus bi. And so, a is the real part of the complex number and b is the imaginary part. Alright? B is the number in front of the I. Alright? So look at this now. This is a complex number. We can all agree. Right? Because we don't know what this is. If you put this in a calculator, you get math error. But we know that the square root of negative 1, we don't know what that value is, so we call it I. Alright? We don't know what that value is, so we call it I. When we call that I now, we end up with this. This is a complex number. It has a real part and an imaginary part. So, just to write down a complex number again, we had z is equal to negative a half plus, just to use a plus root 3 over 2 times I. Alright? In a case like this, we'd say that the complex number, what is the real part of the complex number? Negative a half, yeah? And what is the imaginary part of the complex number? Root 3 over 2. Good. So this is how you'd write it. You'd say that the real part of the complex number z, RE in bracket z, mean the real part of the complex number z. The real part of the complex number z is negative a half, and the imaginary part of the complex number z is equal to root 3 over 2. That's it right there. So let's try another one. What if I give you a complex number z is equal to minus 5 plus 2i? So try and tell me what's the real part, what's the imaginary part. Hopefully, we'd have said that the real part of z is the negative 5 and the imaginary part of z is equal to positive 2. Alright? It's just the number before the I. Alright? Beautiful so far. Beautiful, beautiful, beautiful. Now, not all the time it's going to be that simple. This is where the powers of I are extremely important. The powers of I are extremely important when we're going to be looking at finding the real part and the imaginary part of complex number. So if I give you one last one to try, if I tell you that z is equal to, negative 5 minus 3i, you can tell me that the real part of z is, the real part of this complex number is negative 5, yeah? And the imaginary part of this complex number is, as you rightfully said, negative 3. Now look at this now. Sometimes they can give you a complex number like this. Now look at that. That's difficult. You're probably looking at that and saying, well, I don't see the real part and I don't see the imaginary part, right? Looking at this, we don't see the real part and we don't see the imaginary part. This is where the powers of I is extremely critical. So let's review the powers of I. So just to review the powers of I, we said that I is equal to the square root of negative 1, alright? And so if we square both sides, then I squared is equal to the square root of negative 1 all squared. And the square cancels the square root, and so I squared is just negative 1. Now what about I cube? I cube is going to be I squared times I. And so what we're going to have is I squared is negative 1. Negative 1 times I is minus I. What about I to the 4? I to the 4 is I squared times I squared. So that's minus 1 times minus 1, which is 1. So just to remember, these 4 are extremely important to know. If you don't remember the rest of powers of I, as we did previously, you must remember these 4. So I is equal to the square root of minus 1. I squared is negative 1. I cube is negative I. And I to the 4 is positive 1. Remember these and you're sweet. So now let's continue, and I'm going to put some more and we're going to write down the real part and the imaginary part. Bruh. Let's say they give you this complex number z is equal to 3xy I squared minus 3y I cube plus 5y squared I. And they say write down the real part and the imaginary part. So take 5 seconds. State the real part. Alright. Now let's go ahead and try this now. So we're gonna write down the real part. So first thing, we need to remember that I squared is negative 1. I squared is negative 1. So this can become z is 3xy multiplied by negative 1 minus 3y, but I cube is minus I. So that's minus I plus 5y square I, that's just 5y square I. Now, minus times positive make everything just minus. So z is now minus 3xy. Then minus and minus become plus, so that becomes plus 3y plus 5y square I. Now look at this. These two have I in it. So we can factor out the I. So we have, this is now 3xy with the minus in front of it. Plus, factoring out the I, we have 3y plus 5y squared. So now you have it in standard form. Anytime you want to be able to can tell them the real part, you have to put it in standard form. So now we know that the real part of z is equal to negative 3xy, and the imaginary part of z, now we can tell them that is 3y plus 5y squared. Nice. Now we can tell them the real part and the imaginary part. Beautiful. Alright, let's just try one last one with stating the real part and the imaginary part. Or two more rather. What if I gave you z is equal to cos cube theta I to the fifth minus 5 cos squared theta I to the 4 plus 3 cos theta I. What if I gave you that and asked for the real part? Now, I to the fifth, you probably say, wait, I to the fifth? Go ahead and attempt it. So 5 seconds, pause and attempt. So I to the fifth, bear in mind I to the fifth is equal to I to the 4 multiplied by I. But I to the 4 is 1 multiplied by I. So this is just I. So now we can say z is just cos cube theta I minus 5 cos squared theta times I to the 4 is 1. So put times 1 plus 3 cos theta times I. Now we just need to group I them together and put the real part first. So put in the real part first, that's minus 5 cos squared theta. That's minus 5 cos squared theta. Then we have cos cube theta plus 3 cos theta in terms of I. So that's plus cos cube theta I plus 3 cos theta I. Alright, so now we can factor out I. And we have cos cube theta plus 3 cos theta times I. And put back your real part. Minus 5 cos squared theta. So now you can tell them your real part and imaginary part. So now we can say the real part of the complex number z is minus 5 cos squared theta. That's the real part. And the imaginary part is this right here. The imaginary part is cos cube theta plus 3 cos theta. So the imaginary part of z is cos cube theta plus 3 cos theta. Alright? So always remember the standard form of a complex number is z is equal to a plus bi, where the real part of z is a and the imaginary part of the complex number is b. Alright? And that's it. Beautiful. Now we're going to start the real thing now. So the same way, when you have regular numbers, what do you normally do with regular numbers? You learn how to add regular numbers, you learn how to subtract regular numbers, you learn how to multiply regular numbers, we learn how to divide regular numbers, or we learn how to square root regular numbers, right? In the same way, when we get complex number, we're going to have to do the computations with all of them. So we're going to need to be able to add complex numbers, subtract complex numbers, multiply complex numbers, divide complex numbers and square root complex numbers. With that being said, we're going to start with the easiest one, which is addition and subtraction. That's the basic binary operator that we do, right? That's the first binary operations that we do, addition and subtraction. Alright, so this is the general rule for addition of complex numbers. To add two complex numbers together, we add their real parts together, and we add their imaginary parts together. To add two complex numbers, we add their real parts together, and we add their imaginary parts together. Alright, so here is the general rule being displayed. The first complex number z1 is a plus bi. The second complex number z2 is c plus di. What is z1 plus z2? To add these two complex numbers together, z1 is a plus bi plus z2, which is c plus di. We'll add them together. So we add their real parts, a plus c. Those are the two real parts. Then we'll add their imaginary parts together. The imaginary parts are b and d. So b plus d, we'll put a bracket around it, times I. And that's it. Now, it's always easy to use numerical values, so let's use some numerical values. Let's say we're given the complex number. Let's say we're given the complex number z1 is equal to negative 5 plus 6i, and we're given z2 is equal to 3 minus 4i. And they want us to add z1 plus z2. Alright? They want us to add z1 plus z2. So z1 plus z2, that's just going to be equal to negative 5 plus 6i plus 3 minus 4i. Now, in the same way, how we do addition with algebraic terms is the same way we add complex numbers. So we add the number part them together. Alright, so in algebra, they tell us to add like terms. It's the same way we're just adding like terms. Negative 5 plus 3 plus, we'll add 6i plus minus 4i. 6i minus 4i. Minus 5 plus 3, that's going to be negative 2 plus 6i minus 4i, that's just 2i. So in this case, z1 plus z2 is going to be minus 2 plus 2i. And that's how we add two complex numbers. Now, let's give another example. So I'm going to give another example and you attempt it. Hey! So let's say they gave you this example. z1 is equal to minus 3 plus 2i, and z2 is equal to minus 7 plus 8i. Alright, add z1 plus z2. So go ahead and attempt it. Alright, so attempting it now, we know that z1 plus z2, that's going to be equal to negative 3 plus 2i plus negative 7 plus 8i. Alright? So add their real parts together. Negative 3 plus negative 7, that's negative 10, plus, we'll add their imaginary parts. 2i and 8i is 10i. Alright? Nice. And that's z1 plus z2. So z1 plus z2 is negative 10 plus 10i. Alright? So if you add this correctly, you're doing great so far. You can just do the champion dance. Champion. Alright? You're doing good so far. Lovely. Alright? Now, Let's look at now subtraction of complex numbers. Alright, so to subtract two complex numbers, it's pretty much the same thing. This time we're just taking the difference between the real parts and their imaginary parts. That's all we do to subtract two complex numbers. So to subtract two complex numbers, we take the difference between their real parts and their imaginary parts. Alright, so if they give you z1 is a plus bi and z2 is equal to c plus di, from these two, then z1 minus z2 will be, we take the difference between the real and the imaginary. So it would be a minus c plus b minus d times I. That's all we do to subtract two complex numbers. Pretty much the same thing as when we're adding. So let's look at an example. Let's say they tell us that we're not using z1 and z2 no more. Let's use v and w. If they give you a complex number, v is, let's say, 5 minus 3i, and they give you a complex number, w is equal to, let's say, 12 minus 13i. And they said to find out what is v minus w. Find v minus w. So to subtract these two complex numbers, what is v? v is 5 minus 3i minus w, and w is what? 12 minus 13i. Now when you're subtracting, please expand in the minus sign. When you expand in the minus sign, this part is going to become v minus w is 5 minus 3i minus 12. Minus and minus become plus, and then that's now plus 13i. Ah, beautiful. So look at this. So v minus w in this case is 5 minus 12. 5 minus 12 is negative 7. Minus 3i plus 13i, that's plus 10i. Alright? So you have to remember with subtraction, you have to be very careful. Because when you're subtracting with a bracket, you have to expand the minus inside the bracket. So always put a bracket around the whole thing that you're subtracting. Please put a bracket around the whole thing that you're subtracting. If you don't put the bracket, you can make a big mistake. You can then look at this as minus 12 and then say minus 13, right? So put a bracket around it so you don't make any mistake. We get to see that is minus and minus become plus. Alright? So just for reiteration, let's do one more question. So I'm going to give this one for you to do. So let's say z1 is 3 minus 4i and z2 is equal to, let's say, 4 plus 6i. And then they ask you to find out z1 minus z2. Again, go ahead and attempt it. Alright, now z1 minus z2 is just going to be 3 minus 4i minus z2, which is 4 plus 6i. So do our subtraction, expanding the minus sign, this becomes 3 minus 4i minus 4 minus 6i. When you expand in the minus, in this case, everything becomes minus. Now 3 minus 4 is negative 1. Alright, so group the real parts then. Let's not even skip the steps, see it here. We just group the 3 and the minus 4. And then we'll group the imaginary parts then together, the minus 4i minus 6i. Alright? So 3 minus 4 is negative 1. Minus 4 minus 6i, that's minus 10i. So that's your answer, minus 1 minus 10i. That will be z1 minus z2. Alright, so I hope everybody got that when they tried it. Nice. Okay, lovely. Alright, and now we're going to be looking at multiplying complex numbers. So to multiply complex numbers, there's always two types of multiplication. You can multiply a complex number by just a constant. You can multiply a complex number times another complex number. So the first one we're looking at is multiplying a complex number by a constant. To multiply a complex number by a constant, we multiply both the real part and the imaginary part of the complex number by that constant. For example, let's say z1 is equal to 5 minus 3i, right? You need to multiply it by a constant, 7. Alright, so 7z1 would be equal to, what we're going to have to do is multiply this entire complex number by 7. So you put 7 in bracket, 5 minus 3i. Yeah, 7 times z1 is 7 times a whole complex number. 7 times 5 is 35, minus 7 times 3 is 21. So in this case, 7z1 is going to be 35 minus 21i. And that's it for multiplying a complex number by a constant. Very, very easy to multiply by a constant. So just another one for you to try. Maybe they give you z2 is minus 6 minus 4i. What is 4z2? 4z2. So work that out. We just multiply both of them by 4. 4 times 6, that's 24. So this would be negative 24. And 4 times minus 4, that's minus 16i. So that's 4z2. Alright, so that's when you multiply a complex number by a scalar. When you multiply it by a scalar just means constant. Now how do we go about multiplying two complex numbers now? Now this is where it gets nice, multiplying two complex numbers. Now to multiply two complex numbers, we're pretty much going to do just regular expansion. Alright? We're just going to do regular expansion. In the same way how you multiply two algebraic terms, is the same way you multiply two complex numbers. So the best way to do it is with examples. So look at this. Let's say you have z1 is the complex number a plus bi. And we have z2 is the complex number c plus di. To multiply two complex numbers, if we want to find z1 times z2, we're just going to have to multiply them, a plus bi times c plus di. Now what would we do when we're multiplying something like this? From c set base, right? What we would do is we multiply a times all of this, so a times what's in this bracket, c plus di, and then plus bi times what's in this bracket, c plus di. Then we expand and simplify. After you do this step, you then expand and simplify. And that's all we do in order to multiply two complex numbers. And of course, we expand and simplify to put it back in its standard form. So let's look at an example right here. Let's say we're given the complex number z1 is equal to 5 minus 3i, and we're given z2 is equal to 2 plus 3i. Alright? And they ask us to find z1 times z2. z1 multiplied by z2. Now, if we're going to find z1 times z2, we just multiply 5 minus 3i times 2 plus 3i. To do the multiplication, we expand the bracket. 5 times this, 5 times 2 plus 3i. Then this is a minus 3i in bracket 2 plus 3i. So we go ahead and multiply then. 5 times 2 is 10. So that's 10 plus 5 times 3 is 15. So that's 15i. Minus 3i times 2, that's minus 6i. And then minus 3i times minus 3i, that's minus 9. Now, 3 times 3 is 9, but I times I is I squared. I times I is I squared. Now, what was I squared again? I squared was negative 1. You see the powers of I is very important. The powers of I are extremely important. You have to remember, I squared is negative 1. Don't ever, once we're doing complex numbers, don't ever forget the powers of I. Please, don't ever forget the powers of I. So since I squared is negative 1, this is just going to be I squared is minus 1. So this is 10 minus 9 times minus 1 plus, now 15i, this part now, 15i minus 6i, that's just 9i. So in this case, minus and minus become plus, minus 9 times minus 1, that's plus. So now we have 10 plus 9 plus 9i. 10 plus 9 is 19. That's 19 plus 9i. So that's going to be z1 times z2. Alright? Oftentimes they don't use the times symbol. Oftentimes they're just gonna write z1, z2. z1, z2 means the product. Alright? If we don't put any symbol between it like plus or minus, it just means find the product. z1 times z2, 19 plus 9i. That's it. Alright? So of course, you know the usual, I'm going to put one now for you to try. Hey! Let's say you're given now z1 is equal to, let's say 1 minus I, and z2 is equal to, let's say 1 plus 2i. Alright? Work out z1 times z2. So work that out for me. Pause and attempt. Alright, let's go ahead and attempt it now. So to multiply z1 times z2, we have 1 minus I, and that is multiplied by 1 plus 2i. Beautiful. So we're going to expand them now. 1 times 1, so we have 1 times 1 plus 2i, and then we have minus I times 1 plus 2i. 1 times 1, 1 times anything is itself. 1 times 1 is 1, plus 1 times 2i is 2i, minus I times 1 is minus I times 2i is minus 2i squared. So that's z1 times z2 so far. Alright? Lovely. But remember, I squared is what? I squared is negative 1. This right here says negative 1. So grouping up the numbers them together, this is 1 minus 2 times negative 1. Yeah? And then the imaginary parts them together, 2i minus I, that's just I. Alright? And so what you get is z1 times z2 is equal to 1 minus 2 times minus 1. Minus 2 times minus 1 is 2. 1 plus 2 is 3. So this works out to be 3 plus I. That's it. Now guys, tell me, isn't pure math beautiful? Starting out with something complex, and we reduce to something simple. Pure math is just beautiful. That's it, and that's how we multiply to complex number. Nice. Alright, so now we're going to look at dividing two complex numbers. Now whenever you're dividing two complex numbers, there's something critical that we need to know about, which is complex conjugates. We need to know about complex conjugates. Alright, so just to refresh our memory of conjugates, remember when you were doing surds in Add Math and Unit 1, right? When we're doing surds, right? Something like 1 plus 2 root 2, right? This is a surd. And then you would say that the conjugate of this surd is 1 minus 2 root 2, right? And if you get another surd like root 5 minus 1, this is the same as saying minus 1 plus root 5. And so the conjugate of this would be minus 1 minus root 5. Right? Yeah, man. It's the same way complex numbers have conjugates. Complex numbers have what's known as conjugates. Alright? So first we're going to have to talk about complex conjugates. Complex conjugates. So the conjugate Alright, so that's it. So the conjugate of a complex number is often denoted by Z star or Z prime. You're going to say Z star or Z prime. That means conjugate Z star or Z prime. Alright? Whenever you're given a complex number A plus BI, then the conjugate is A minus BI. Alright? Whenever you're given a complex number in the form A plus BI in standard form, the conjugate is A minus BI. Let's look at some examples. Alright? So, if I give you a complex number Z is equal to 2 plus 4i, then what's the conjugate? Z star. Z star is going to be, so this is the complex number, and over here is the conjugate. So if you have 2 plus 4i, you don't, guys, don't look at the real part. Don't look at the real part. Put back the real part as it is 2. But then, if this is plus 4i, then the conjugate is going to be minus 4i. That's it. You just change the sign in front of the imaginary part. What if they give you z is equal to 3 minus 7i? What's the conjugate? Absolutely right. So if you said this, then you're absolutely right. 3 plus 7i is then the conjugate. Alright? This will become the conjugate. Let's try a couple more. Let's say they gave you z is minus 4 minus 6i. What would be the conjugate? So if you said this, z star would then be minus 4, put back the real part, then just put plus 6i. That would be the conjugate. So all we do for conjugate is we change the sign of what's the imaginary part. So the sign in front of the imaginary part, we change that. So if it's a minus here, we'll put a plus over here. If it's a plus here, we'll put a minus for the conjugate. That's it. Now what does conjugate have to do with dividing complex numbers? Well, conjugates have everything to do with dividing complex numbers. So anytime you're given a complex number, given the complex number, let's say z is equal to a plus bi over c plus di, right? So in order to simplify this complex number, because really and truly this is a complex number given by one complex number over another. In order to simplify this complex number, when we're dividing complex numbers, right, what we do is we rationalize by the conjugate of the denominator. We rationalize by the conjugate of the denominator. So in this case, what we will do is multiply by, what's the conjugate of this denominator? C minus di. So all we do is multiply by the conjugate of the denominator and then simplify. That's all we do to simplify when we're dividing two complex numbers, alright? Because think about it, this is just a complex number in the numerator being divided by the complex number in the denominator, but we need to get it in standard form. So we do the division, and to do the division we have to multiply by the conjugate of the denominator. It's just like surds, right? If you have a surd 1 over 1 plus 2 root 2, you'd have to multiply the numerator and the denominator by 1 minus 2 root 2. That's how we end up simplify this, right? So it's the same thing with complex numbers. So let's look at an example. Alright, so let's say you're given 3 minus 4i over 1 plus 2i, right? And you need to simplify. So simplify this. So to simplify this complex number, we're going to have to start by saying we have z, which is 3 minus 4i over 1 plus 2i. The conjugate of this is multiplied by 1 minus 2i over 1 minus 2i. Beautiful. Now since this is a conjugate, what are we going to do? Since this is a conjugate, whenever you're multiplying two fractions, we multiply across their numerators and we multiply across their denominators. But just bear this in mind. When you're multiplying across their denominators, please remember this, guys. Let me put in brackets here. A plus b times a minus b is a squared minus b squared. Guys, you see how C-set knowledge important? A plus b times a minus b is a squared minus b squared. A plus b, a minus b. A is 1, b is 2i. Difference of two squares is going to apply. So let's multiply these. So z is going to be 3 times 1 is 3. 3 times minus 2i is minus 6i. Minus 4i times 1 is minus 4i. Minus 4i times minus 2i. Minus times minus becomes plus. 4i times 2i, that becomes 8. I times I is I squared. So multiply the numerators so far. Then you can multiply the denominators. Even if you don't want to remember difference of 2 squared, 1 times 1 is 1. 1 times minus 2i is minus 2i. 2i times 1 is plus 2i. And then 2i times minus 2i, 2 times 2 is 4. So that's minus 4i squared. Beautiful. Now this part is 0. Minus 2i plus I, 2i, that's 0. So what we get now is, look at this now. Minus 6i minus 4i is minus 10i. But I squared is what? Negative 1. I squared is negative 1. So this is negative 8. So this is 3 minus 8. And then this is minus 10i. That's what we have. This is minus 8. Then in the denominator, I squared is negative 1 again. Negative 1 times negative 4 is positive 4. So we get 1 plus 4. So this works out to be z is equal to 3 minus 8 is negative 5 minus 10i over 1 plus 4 is 5. Beautiful. Now guys, look at this, look at this. Can't we divide each term by 5? Absolutely. We can go further and break it up to get that this is negative 5 over 5 minus 10 over 5i. Now negative 5 over 5 is negative 1 minus 10 over 5 is negative 2. So that's your answer. All of this works out to be minus 1 minus 2i. That's it. Alright? So this complex number up here, when we divide it and put it in standard form, this is minus 1 minus 2i. That's our answer. Beautiful. Alright, so we know the drill already. Gonna put one more for you to try now. Bruh. Put something very simple. Simplify 3 plus I over 1 minus I. Very easy. So if we're told to simplify this, what do we start with? Yes, we start by. So wait, before we do it, go ahead and pause and attempt it. Pause and attempt. So pause and attempt. Alright, now let's go now. So we have 3 plus I divided by 1 minus I. So multiply by the conjugate, which is 1 plus I. It's always a conjugate of the denominator we multiply by. So that's the first step. Now we multiply across our numerators. So this is going to become, it is 3 times 1 plus I times 1 plus I. Then in the denominator, 1 times 1 is 1. 1 times I is I. Minus I times 1 is minus I. Minus I times I is minus I squared. Good. Expanding out the numerator, 3 times 1 is 3. 3 times I is 3i. I times 1 is I. I times I is I squared. Over, now the plus 1 and the minus 1 cancel, that part is 0. But I squared is negative 1. But minus negative 1, this is minus negative 1. Minus and minus become plus. 1 plus 1 is 2. So the denominator becomes 2. Now I squared is negative 1. So this becomes 3 minus 1. Because this is now saying 3 plus 3i and I is 4i. 3i and I is 4i right here. And I squared is negative 1. So this becomes 3 plus 4i minus 1 over 2. Beautiful. Now 3 minus 1 is 2. So that works out to be 2 plus 4i over 2. Then we can divide the numerator and the denominator by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. Alright? And that's that complex number right there. So you can write, therefore, 3 plus I over 1 minus I is the same as 1 plus 2I. And that's it. Alright? Nice. Now when you get to this stage, please, I don't want anybody to make this mistake. This is a common mistake reported by Cape. Students will do this. 2 into itself 1, 2 into this 1. And then write 1 plus 4i. Please don't do that. Please don't do that. Don't ever do that mistake. Alright? That's a big common mistake that is made on Cape exams. We don't want to make that mistake. Alright? Think about it this way. This popular mistake that is made, Think about it this way. 10 plus 8 divided by 2. 10 plus 8 is 16. 16 divided by 2 is 8. Right? But if you were to just cancel the 2 from one side of it, then what you're saying is 10 divided by 2. If you cancel it, this is saying 1. 2 into this 5. 5 plus 8 is 13, but 13 is not 8. So look at it, that method cannot work. You have to divide both the numerator and the denominator by 2. Alright? So this is how we divide complex number. And there's one final thing to go, which is finding the square roots of complex number. Alright, so we're almost done with